Simply put, the signal that we get and look at in clinical MRI comes from imaging hydrogen nuclei in water and in fat. These hydrogen nuclei, like in other subatomic particles, possess spin or spin angular momentum. And this spin gives the nuclei a magnetic moment. To put it in a simpler way, think of each hydrogen nucleus behaving like a tiny bar magnet with a vector illustrating the magnetic moment. In the absence of an external magnetic field, all of these tiny bar magnets are pointed in all different directions. And if you look at the net magnetization vector of any particular tissue, it would be about 0. There would be no net magnetization vector in any direction. In an externally applied magnetic field, however, like an MRI machine, the tiny bar magnets tend to want to align with the magnetic field. So in a tissue, you end up with more magnetization in the direction of the magnet. The tissue has a net magnetization vector in the direction of the main magnetic field, as shown here. Let's look at an MRI machine. So a big part of this MRI machine acts essentially as a big magnetic field that is aligned down the bore of the magnet, and that's marked here as B0. The main magnetic field is down the bore of the magnet, which is also called the Z-axis or Z-axis. The strength of the magnetic field in clinical MRI these days is most commonly 1.5 or 3 Tesla. And this diagram shows these magnetic moments of the individual hydrogen molecules aligning with this field. Since the majority of them align, these add up to a net magnetization vector in the direction of the main magnetic field. When a magnetic moment is aligned in the field like we're showing here, this is considered a low energy state. Put more simply, the little bar magnets are naturally pulled in this direction along the z-axis or z-axis. It's easier for them to align with the field than to oppose it. The z-axis, again, is the longitudinal direction down the bore of the magnet. So, how do we translate this into MRI signal? Next, we apply something called a radio frequency pulse or RF pulse that is designed to tip the net magnetization away from the z-axis. The RF pulse is essentially a smaller, varying magnetic field applied at a specific frequency in a direction that is perpendicular to the main magnetic field. It's not really a radio wave, but instead it's electromagnetic energy with a frequency that is in the radio wave spectrum. A key point is that in order to tip the magnetization away from the z-axis, the RF pulse has to be at a frequency that matches the spin of what it's trying to tip down. For now, who cares about these details? What matters most is that the RF pulse tips the net magnetization away from the z-axis and into the xy plane. How much it tips away from the z-axis is called the flip angle. Here, for simplicity, let's say that this is 90 degrees for now, and again, with this 90-degree RF pulse, shown here with B1, the net magnetization is tipped into the xy plane, again perpendicular to the z-axis that we described prior. The RF pulse does two things. One, it tips the net magnetization vector into the xy plane, as we just showed in this diagram. And two, it also makes most of the hydrogen nuclei start to precess in phase at a particular frequency. Think of precession as like a wobbling motion or spinning of an object like a top. The particular frequency that protons precess at is called the Larmor frequency, which is calculated by this Larmor equation. The equation says that the frequency here, F, is determined by the magnetic field, or B0 here. The stronger the magnetic field, the faster it precesses in sync after the RF pulse. The frequency also depends on the nucleus itself, which is reflected in this term here, gamma, which is the gyromagnetic ratio. If that's too much for now, just remember that the RF pulse does two things. It tips the magnetization into the XY plane from the Z-axis and causes the protons to precess or wobble in sync in a particular or at a particular frequency. Another important point to realize is that we generally detect MRI signal in the XY plane with a coil, essentially a coil of wires. We know from basic physics that if we put any coil of wires in a varying magnetic field, this is going to create a measurable current in the coil. So in MRI, a net magnetization vector tilted into the XY plane, like we've shown on this MRI diagram here, if the detector was down here, we have a net magnetization vector in the XY plane that is precessing in the XY plane. So it's pointing towards, then away, then towards the coil. And that varying magnetic field is going to create a current in the coil, and that's where we get the MRI signal. Let's look at that in another way. Instead of looking at it in the magnet or on an MRI diagram, we can look at it on this XYZ Cartesian system. So again, the magnetic field here is in the direction of the Z-axis, which is down the bore of the magnet. The net magnetic moment is going to be in the direction of the main magnetic field, shown here as a blue arrow. An RF pulse is applied at the right frequency and at a particular flip angle, here 90 degrees for simplicity. And again, it's going to do two things. One, it's going to tilt the net magnetization vector into the XY plane. And two, the protons are going to precess in sync with each other, so the entire net magnetization vector is precessing in the XY plane, as illustrated here. And as mentioned earlier, we detect signal in the XY plane with a coil detector. The varying field in the XY plane towards, then away, then towards, and as it precesses is going to create a varying magnetic field that's going to create a current in this coil, which is the MRI signal itself. So this is all great. We understand how we get MRI signal. So again, after the RF pulse, we've tipped our net magnetization into the XY plane. And as we showed earlier, the nuclei are also precessing like a top at a particular frequency in sync in that plane. This doesn't happen forever, and over time you start to lose your signal. Over time, through interactions with the surrounding environment, the net magnetization vector will relax back to the Z-axis. Remember, the Z-axis is the longitudinal axis, so this process is called longitudinal relaxation, also known as T1 relaxation. At any given point between the XY plane and the Z-axis, there's going to be a net magnetization vector with a Z-axis component or longitudinal component and a transverse component in the XY plane. What matters here is that depending on the tissue environment, the net magnetization will relax back into the Z-axis at different rates. So at any given time, different tissues will have different amounts of detectable signal and can be differentiated based on this. If the vector hasn't recovered all the way back into the Z-axis, it has a partial longitudinal component. If we apply another RF pulse when it has a partial component, the resultant net magnetization in the transverse plane will be equal to the amount of the Z-axis component just prior to the RF pulse. This is important because, as we mentioned, we detect signal in the XY plane. So in order to detect differences in T1 relaxation, we need to allow them to relax at different rates in the Z-axis and then apply an RF pulse and listen in the XY plane. A separate but related process is transverse relaxation, or T2 relaxation. Remember, we also mentioned that after an RF pulse, not only do we tip the net magnetization into the XY plane, but the hydrogen nuclei also start to precess in the XY plane in sync. In order to maintain signal in the XY plane, or in the transverse plane, the precessing molecules have to 1. Remain in sync as they precess, and 2. Stay in the XY plane. So, over time, the transverse signal goes away, which is called transverse relaxation, or T2 relaxation. In this diagram we have here, we have the Z-axis pointing upwards, and that's again the magnetic field direction. And over here we have the XY plane that's flat. And early on we have a single line here that represents all of the precessing molecules in sync. And the red line here is the net magnetization vector that shows full signal at the beginning here. Over time, so this yellow line here represents time, over time the nuclei begin to lose their phase coherence, and they precess slightly out of phase and eventually lose signal in the XY plane. In other words, they relax in the transverse plane, transverse relaxation, or T2 relaxation. This is based on interactions of the hydrogen nuclei with the molecular environment, and it's also referred to as the true T2 effect. A key point that might not be immediately apparent is that anything that causes T1 relaxation, as we showed here, and moves into the Z-axis, or moves the magnetization towards the Z-axis, is always going to result in a concomitant loss of transverse magnetization. If all of the magnetization was in the Z-axis, then the transverse component is going to be 0. In other words, any T1 relaxation is always going to cause or be accompanied by T2 relaxation. But there are other additional interactions that can also result in more T2 relaxation, as illustrated in this diagram down here, where we lose phase in the XY plane. Remember, the precession has to remain in phase to keep transverse signal, so there is further loss of signal when they lose phase coherence. Knowing this, we can see that the T2 relaxation is always less than the T1 relaxation. In other words, T2 relaxation happens more quickly because, again, anything that causes T1 relaxation also causes T2 relaxation, plus loss of phase coherence causes T2 relaxation. So T2 times are always lower than T1 times. Again, don't lose sight of the main point here if none of that made sense. The main point here is that different tissue environments result in different relaxation rates, and therefore different tissues can give us different amounts of signal, and they look different on imaging. I should mention that T2 refers to true T2 effects due to energy transfers with the tissue environment. Again, the mechanisms aren't important, but what is important is the concept of T2 star. T2 star refers to observed transverse relaxation, which includes the effects of magnetic field inhomogeneities. Remember earlier we mentioned that hydrogen nuclei precess at a particular frequency, the Larmor frequency, that was directly proportional to the magnetic field strength. Any magnetic field inhomogeneity will result in some protons that experience higher field strengths and others with lower field strengths. So the ones that have higher field strengths precess faster than the other ones. If that happens, then, of course, you know that there will be a resultant loss in signal in the transverse plane very quickly because the transverse magnetization depends on precession remaining in sync. Local field inhomogeneity can be caused by things like metal, calcium, hemosiderin, all things that affect the magnetic field that hydrogen nuclei around these things experience. As a result, things around the metal, for example, will lose T2 signal very quickly and show up as very dark on these images. T2 star is always going to be shorter than true T2 because T2 star is just the T2 effect plus the effect of the magnetic field inhomogeneities. Before I go on, if you have no MRI background and are lost right now, that's okay. Just stick it out. We'll get to more clinically relevant things relatively shortly. If you take one thing away from the last few slides, it should be this. Any given tissue has a particular T1 relaxation time, namely how fast it recovers magnetization of the z-axis, and a T2 relaxation time, how long it takes for transverse signal to decay. And we can differentiate tissues based on this, which is the whole point of imaging. Now, in order to create MRI images, the MRI goes through a complex set of precisely timed manipulations, RF pulses, gradients, etc., called pulse sequences. We're going to go over some pulse sequences commonly used in abdominal imaging in the next section. But these pulse sequences are what are run to get you all of the images that you end up looking at on the workstation. The pulse sequences can result in images that are T1 weighted or T2 weighted, which describes which characteristics of the tissue we're trying to look at. Are we trying to differentiate tissues based on their T1 relaxation or their T2 relaxation? No sequence is purely T1 or T2 weighted, but a pulse sequence is designed to try to bring out the T1 or T2 characteristics of each of the tissues to differentiate them. And we'll briefly talk about how that happens in the next section. So let's start diving into what tissues are going to look like on these T1 and T2 weighted images that you're going to be looking at, using the concepts that we've learned of relaxation. Remember, in MRI, we're really only imaging hydrogen atoms in water and in fat, mostly water. So let's start by considering pure water and pure fat. Here we have water and fat hydrogen atoms. Yellow is fat and blue represents hydrogen and water. And they are aligned with the external magnetic field in the longitudinal or z-axis. We apply a 90-degree RF pulse, and the net magnetization vector is knocked down to the xy plane and precesses in sync in the xy plane. Water has a very long T1 relaxation time, so it likes to stay closer to the xy plane for a long period of time. Fat, on the other hand, has a short T1 relaxation time, so it recovers towards the z-axis pretty quickly. Fat now, after some time, has a much larger component than the water in the z-axis. The fat has recovered quite a bit more in the z-axis. So when we apply another RF pulse at this point again, the fat is going to have a lot more signal than the water. On pulse sequences that are T1 weighted, fat is going to be very bright, and water is going to look relatively dark. Similarly, it takes a long time for the T2 signal of water to decay, so you maintain your water signal on T2 images for a long time. On T2 weighted images, water looks very bright. Fat is a little more complex, so we won't talk about fat on T2 for now. What about all of the other tissues? What are they going to look like on MRI? So again, MRI is looking at hydrogen molecules in water and in fat. And we talked about pure water and pure fat on the last slide. We've also displayed these in the first two rows, so pure water and pure fat. So water is going to be T1 relatively dark and T2 pretty bright or very bright. Fat is going to be bright on T1 weighted images. It's more complex on T2 weighted images, but for fast spin echo or fast T2 weighted images, fat is going to look relatively bright. In other tissues in the body, like the liver or the pancreas or other tissues, we're not really dealing most of the time with pure water or pure fat. Instead, the hydrogen molecules in water and in fat, mostly water actually, are in an environment of other macromolecules. These macromolecules are going to affect the T1 and T2 relaxation times of the hydrogen molecules in the water in those tissues. So we're still imaging the water, for example, in the liver, but the T1 and T2 relaxation times are severely affected by the macromolecules that are in the liver. That's why in a normal liver, the T1 signal is relatively bright and the T2 signal is relatively dark. As an aside, most lesions that you're looking for, or a lot of lesions that you're looking for in the liver, are going to be T2 brighter than the T2 dark background liver, so they're going to stand out in comparison. Similarly, on T1 weighted images, most lesions are going to be relatively T1 dark compared to a brighter liver. But we'll talk about that more in the liver MRI video. Most pathology in general is going to have a high water content, so it's mostly going to be T1 darkish and T2 brighter. It's worth knowing a few commonly seen things that do not follow those signal characteristics. For example, the signal of blood products depends on the age of the blood products. But for now, and especially in body imaging, we're often looking for subacute blood, and it's often going to show up as T1 hyperintense or T1 bright. The T2 signal in blood is going to depend on when you're imaging it. This is similar to proteinaceous material and mucinous material. More proteinaceous and mucinous materials can be T1 bright and T2 darker, especially when the mucin becomes very dry or inspissated. Hemosiderin or chronic blood products are going to be dark on all sequences, so dark on T1 and dark on T2. And very fibrotic tissues are also going to be dark on T1 and T2 weighted images. There's not much water in densely packed fibrosis. Lastly, not on this diagram, but air and metal are going to look completely black on all sequences because there are no water or fat hydrogen nuclei in either. If this is confusing you, don't worry. After we get through this introductory stuff, we're going to pull up some MRIs and review all of this stuff again. For now, look at this image. This is a T2 weighted image through the upper liver. You see the CSF is bright here. That's almost like pure water. This is a T2 weighted image. Fat is bright here. The fluid in the stomach is bright. The liver is relatively dark. And we have a focal lesion here that is relatively bright. This happens to be a hemangioma. But notice how good MRI is at contrasting the background liver to the focal hepatic lesion.